All right, welcome. This is going to be the Unit 5 Radicals Review homework help video. My first piece of advice is do not use this as your only study aid for our Unit 5 test. Because I've posted videos for every homework, I'm going to skip over some topics that I have posted videos for and really focus in on graphing radicals. Just do a couple here and there, but really just want to do some graphing radicals to help you out. Let me just make sure this is recording. Yep, that looks good. All right. I'll start with problem number 3, though. I think this is a good problem to practice with. Now, I'm taking a cubed root. So in order to take a cubed root, I need to break this 16, this negative 16, into a perfect cube. But when I do that, I want to break it into if I can pull out a perfect cube, I want that perfect cube to be the number that's negative. And so 2 cubed is 8. So the perfect cube that fits into 16 is 8, but I'm going to make that a negative 8. Because now if I take the cubed root of negative 8, it'll be negative 2, and I'll be able to pull the negative out from inside of the radical. All right, likewise, I'm going to split up this x to the 8 in a way that gives me as many groups of 3 as possible. So x to the third, x squared. Our product property of exponents states that if I'm to multiply these, I can add them up. So let's just make sure they still add up to 8. 3 plus 3, that's 6, plus 2 is 8. So I've done this in a way that is acceptable. But now when I divide this up into the cubed root of negative 8 times the cubed root of x to the third, I'm going to be able to cancel that cubed with the cubed root. Let me write this out. X to the third times the cubed root of everything we weren't able to take out, which is a 2 and an x squared. All right, and this leads us to our final answer. This here becomes a negative 2. These cancel, these cancel. X times x is going to be x squared, so we've got negative 2x squared cubed root of 2x squared. All right, so yeah, if I see a negative inside of a cubed root, I know that I'm going to be pulling out a negative coefficient. It works that way every time. All right, another problem that would be good. I'm looking for one particular. Let's do 18 really quick. So to solve this, I've got to get this variable n out from underneath the radical. To do that, I can raise both sides to the power of 2. That'll cancel out the radical. And I'll be left with n minus 7 equals 41, or n minus 7 squared equals 41 minus 5n. All right, after I just FOIL this out, I'm going to get an n squared minus 14n plus 49 equals 41 minus 5n. Combine like terms, do some inverse operations like subtracting 41 from both sides, adding 5n to both sides. And I get n squared minus 9n plus 8 equals 0. So I recognize that I've got a quadratic, and the only way to solve the quadratic is to get it equal to 0. Now I can factor. I'm looking for two numbers that multiply to be 8 but add to be negative 9. Those numbers are negative 1 and negative 8. And now zero product property, I get the answers n equals 1, n equals 8. But we're not done, because when we've got equations with radicals, you've got the potential for extraneous solutions. So I have to plug these back in. So 1 minus 7 equals the square root of 41 minus 5 times 1. Let's see if this one balances. Negative 6 equals the square root of 5 times 1. That's just 5. The square root of 36. -6 equals 6. This is not good. Therefore, this was extraneous. Extraneous. All right, let's test out 8 really quick. 8 minus 7 equals square root of 41 minus 5 times 8 is going to be 40. 8 minus 7, well, we'll just say 1 equals the square root of 1. 1 equals 1. This does check out. This is a good solution. So extraneous and a good solution. All right. Looking for another one that we might need to go over. Let's do 29 real quick. 29, block this one out so I can have some space to write. 29's got a couple good properties that we're going to use. So the first thing is that because I've got an equal sign, I'm able to do inverse operations like raising both sides to a power. I can do this in a way that when I multiply that power to this power, I'll get a 1. So if I raise it to -3/5, for example, the power to a power rule says that I multiply both exponents, and they are reciprocal, so they become a 1. So now I've got 1 over 3,125 to the power of -3/5 equals n. All right, now we can use our negative power rule, which states that negative powers flip fractions. So this is just going to become 3,125 to the positive 3/5 equals n. And now we're going to rewrite this in radical form. So the 5th root of 3,125 all raised to the 3rd power equals n. The 5th root of 3,125. I'm just going to hit math 5 to do a 5th root, 3,125, and I get a 5. So the 5th root of 3,125 is a 5. 5 to the 3rd equals n. 125 equals n. And that problem there. All right. Let's see. We did function operations a lot today. Let's do 41 real quick. G of 3x. I can write that as G of 3x with a parentheses like that. So what I do is I plug 3x in for this x here. So this becomes, so I can evaluate G of 3x equals -4 times 3x plus 5, which equals -12x plus 5. And now I can do G of 3x is G of that whole expression there. And now I get -4 times that expression. I plug it in for x, -12x plus 5, plus 5. Distribute, I get a 48x minus 20 plus 5. Giving me a final answer, G of 3x equals 48x minus 15. Hello? Not much, just finishing up a video, then I'm gonna leave. All right, I'll see you there close to, yeah, that'd be fine. Can I call you back in like 5 minutes? All right, talk to you then. Bye. All right, 2 videos in a row, we got a phone call. Sorry. Okay, so when graphing, it's a good idea to sketch in my parent function, which is a line centered at the origin, goes up 1 over 1, and then it's kind of like a parabola turned on its side, so we can remember that pattern 1, 4, 9. But we'll just do that as our x values as we go up 1 more. And so I've got these 3 points here, I'll connect them with kind of a dotted line. And then it goes off the graph. So that's my parent function. Now, this one here has been moved because we are subtracting directly from the exponent. This moves it to the right 4. And then this -3, because it's at the very end, moves it down 3. So I can take those 3 points, move them right 4, down 3. New point. This one here, right 4, down 3. This point here, right 4, down 3. So right there. I can do better than that. So this is our function here in blue. All right. Again, for number 44, I'll add in those points of our parent function, 0, 0, 1, 1, 4, 2. And now I'm going to move these points. This will move it left 5. Or you could think it happens 5 faster, down 2. So each point needs to be moved to left 5 and down 2, left 5, down 2. Left 5, down 2. There was a point out here at 9, 3. If I move it left 5, I get to 4, 3, down 2, moves right there. Just like that. All right, this one here, again, dot in some parent function. Dots will include 9, 3. This one here is going to get a vertical stretch of 2. That plus 3 there, it's always opposite what you think, moves it left 3. This -3 moves it down 3. So here I'm going to apply that vertical stretch first and double the height of every point. See, this one's at 3, so now it's at 6. Then I'm going to apply the shifts. Left 3, down 2, or down 3. For our final, let's do this in a different color. Our final graph, 1, 2, 3, 1, 2, 3. 1, 2, 3, 1, 2, 3. 1, 2, 3, 1, 2, 3. Oh, and I forgot about our point that didn't move when it was vertically shifted. It needs to be over here. So radical graphs always have a starting point. That point is always at h, k. It's always the starting point. So a good double check to make sure you've got the right graph. Let's just do one more of these. We'll skip down to something that's been transformed in a lot of different ways. Oh, we got some cubed roots too. So the parent function of a cubed root graph, it's centered at 0, 0 again, but then goes up 1 over 1. It also goes backwards 1, down 1, because the cubed root of -1 is -1. And then the cubed root of 8 is 2, so we can put a point there. Cubed root of -8 is -2. So that's our parent function. I've dotted in. Now let's see the changes we have to apply to it. We need to do a vertical stretch of 2. This plus 2 is going to move us left 2, and this -3 here is going to move us down 3. Let's apply the vertical stretch first. Add in new points. Point at 0 doesn't stretch at all. These points get twice as tall. All right, and now I need to move each of those points left 2 and down 3. So left 2, down 3. Left 2, down 3. Left 2, down 3. Left 2, down 3. And then this one left 2, down 3, it'd be off the graph about there. Connect those up. It makes an anti-symmetrical graph like that extends off to infinity in either direction. Let's see what I did on 48. Make sure that graph looks about right. Oops. Yeah, looks about right. Notice it is centered at h comma k still. The h value is -2. The k value is 3. I know we wrote it in front, but you just have to move it to the back at the very beginning. -2 comma -3 is that point right there. All right, well, best of luck on graphing those radicals and preparing for the test.